So intro to graph databases. It's always nice to do and nice to sort of kick off with. I think is because lots of people have a partial or maybe even wrong understanding about what graph databases are. When I first started working with Neo and started to explain it to people, and they started, okay, we're talking about graphics, or we're talking about, what are we talking about here? Are we talking about pictures, or, they get it, have a very strange understanding of it. Or you can be, like my dad, when I told him about what I was going to do, he said, I sold exactly the same thing in the 70s. That was that was his reaction. But maybe there's a genetic thing there. So we'll talk a little bit about graphs. We'll talk about graph databases, and we'll spend quite a bit of time talking about, how do you query the graph and how do you interact with it. Obviously, I have a demonstration that we can use for that, and then we'll wrap up and do some pizza and hand over to Tim after that. So yeah, the sort of most common misunderstanding is that these are not graphs, right? These are charts, right? And they are graphics if you want, but they are not graphs. They are not what we are talking about tonight. These are very different things. What we're talking about are networks, right? As invented by this lovely gentleman a long time ago. Does anyone know, I mean, from not you guys, but some of the new people, what Euler was working on? Yeah, you've learned this, right? It's been in your university class, or yeah. Well, yeah, you knew it once, exactly. Yeah, I mean, what he was working on this is a long time ago, was solving a problem for the Emperor of Prussia, which is now known as the Seven Bridges problem, right? The Seven Bridges of Königsberg. And before you start Googling, where is Königsberg, you won't find it immediately because it's called Kaliningrad now. It's on the other side of the Baltic Sea. And it was a medieval city, old city with lots of little streets and alleyways. And basically, the emperor was going to come and visit, right? And the emperor, being the emperor, right? He had some demands, and he basically said, I want to take a tour of the city, but I only want to walk every single street once, right? Because I'm the emperor, right? I can make silly demands, so I'm going to do that one. And so they were trying to solve it, empirically, walking the streets of Königsberg, and couldn't solve it. They couldn't figure it out. So what do? You call up Switzerland and you ask Euler for help. And that's what he did. He worked on this problem and he basically solved it mathematically, right? He figured out a way to calculate whether or not you could solve this problem, right? And in doing so, I think he did two really interesting things that people still do today, every day, with graph databases and with graph technology in general. Is the first thing he did is he basically said, I'm going to take a look at the data in a very different way. I don't want to look at the streets, right? The streets really don't matter that much. There's enough streets, right? What I need to know is how are those streets connected to each other, right? And what are the bottlenecks in this map to get you from one part of the city to the next part of the city. Because this is peculiar about Königsberg, right? Königsberg has 4 parts, right? 4 parts in the city, and they're split by a river, right? Does anyone know the name of the river? Know your Google papers, people? It's the river Pregel, the Pregel paper. This is what this Pregel paper is the paper that invented Big Table, Cassandra and those types of databases, HBase, this is the river Pregel, and it cuts the city into 4 parts, right? A, B, C, and D, right? And those 4 parts are connected to each other by 7 bridges, right? There's actually a model of this city in Christchurch, New Zealand. They have rebuilt it on the university campus. You can go and visit it if you want. It's really crazy. But he was trying to figure out, can I do this walk? Can I do this walk across the city without walking without walking a single street twice? Essentially meaning, don't walk a single bridge twice, right? You shouldn't walk. There's enough streets. We shouldn't walk the bridges twice, right? So he basically forgets about all the streets, creates a different representation of the data, right? Which is essentially a network representation of the data, right? You're looking at the world's first graph. It should have a name, shouldn't it? We should call it something, the Foo graph, something like that. Anyway, so this is the world's first graph, which essentially is something that you can represent mathematically as a matrix. Right? It's an adjacency matrix, right? 4 by 7. If there's a connection, you put, you can very quickly represent this mathematically. That's what he did, right? So he has something to work with now. Now, how do you figure out whether or not this walk is possible? Well, he basically has to apply an algorithm. Right? He has to apply an algorithm to this mathematical notation to figure out, is this possible, yes or no? And the algorithm he came up with is, anyone? No, it's called counting. Obviously, the Dijkstra algorithm is a pathfinding algorithm. It's probably something that you could use to solve this problem as well. But all Euler did at the time was he counted the number of edges. Because that's all you need to know. When you're going to do this walk across the town, you're going to start somewhere, right? Let's say you start at A, right? You're going to finish somewhere, right? Let's say you finish at D, right? So you're going to walk off of A, you're going to walk onto D, but you're going to walk onto B and off of B, right? It's really simple. So that means that the first and the last part of the city can have an uneven number of edges, connections, but the ones in between have to have an even number of edges. Right, so it's really about the degree, what we call the degree of the nodes. Right? So if you count, right, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, you find that it's not possible. It's very simple. Right? But why am I spending so much time on that? Because having this new representation of the data, stepping away from your old data model, which was, this complicated map with all these tiny little alleys, right? And, morphing it into a different representation, which is the network, right? The graph, right? It's a really important step, right? If you want to solve complicated problems, it's probably a very useful step to take. And then secondly, this counting algorithm is probably a really silly example, but there are lots and lots and lots of interesting graph algorithms, network algorithms that allow you to make these types of decisions very, very quickly, much more efficiently than you would be able to do so on another data representation. Does that make sense? Move on, Rick, move on, spending too much time on this. Yes, I know. That's why we're going to talk a little bit about graph databases, right? Because we're going to use that graph model, that graph representation, and those graph algorithms in a new technology. Actually, it's not so new, but we're going to use it in a technology that deals with data. Right? We've been dealing with data for a very long time, and the reason why my dad said, I was selling the same thing in the 70s. He was not kidding, right? He was selling network database, code-to-cell databases on a Philips mainframe and then on a DEC mainframe in the 70s and 80s. And you know what? It's very, very similar. Right? There's a lot of similarities between those two types of technologies. So they've been around for a long time. Neo4j has been around for a long time. I mean, Mikael knows Emil and Johan and Peter from back in the dark ages when they started the project, which was early 2000s, right? I always jokingly say, that's why it's called 4J, because 4J was really hip then. It's a very long time ago, but this is what they did. And they did, so they created Neo4j. Why? Because they saw some issues, some interesting problems in relational databases, which were the dominating data store at the time, still are, right? Relational databases have been good for many different things, but they've also suffered from two main deficiencies for the longest time, and they really haven't been solved. The first one is all about volume, right? It's how you scale those relational databases to, lots and lots and lots of millions and billions and zillions of data elements, right? That is a challenge, right? And that's not a challenge that we're addressing with graph databases, but it's a challenge that has spawned a plethora of new technologies that deal with big data, right? So, very, very useful. Lots of people use it. I think you guys use some document stores, and so you'll talk about that some more. But essentially, that's a very important problem in the relational database world that people are addressing with all kinds of wonderful new technologies. But there has traditionally also, for the longest time, been a complexity problem in relational databases, which is essentially the join problem. Right? How do you deal with complex domains, complex models, and interact with those complex models in a scalable, performance, interesting, meaningful, insightful way? That's a complexity problem that has been lingering for years, and that's really the problem that we're trying to address with graph databases. It's all about those complex queries, right? So this has been around for a long time. That's why these NoSQL and not only SQL databases have been created, and you can sort of categorize them in two buckets, types of NoSQL stores. And I borrowed this slide from Alistair Jones, who created this a couple of years ago, basically saying that in the NoSQL world, you have two types of stores, right? One of those stores addresses the volume problem and essentially does so by creating a simpler data model, right? It creates a simpler data model that is easier to work with, but is also easier to scale out, like the document or the key value pair or the wide columns model, right? It's essentially something that is much easier to scale out, not in the least also because most of those data stores don't care about transactions that much, right? So that's one part of NoSQL. The other part of NoSQL is the part where we are firmly rooted, and that's the graph model, where we actually try to solve a separate problem, a different problem. It's the complexity problem, and we do so by adopting a much richer data model, right? If you think about it, relational databases are not very relationship friendly, right? They are very relational, if that makes sense, or anti-relational. This is actually taking this a step further and going for a much richer model, which places those relationships at the core of the data model. So Neo4j is an implementation of such a graph database, right? It's an online transaction processing database, so it's something that you put between a web request and a web response, right? It's not an OLAP tool, right, which you put between dinner and breakfast, right? This is something that's supposed to be online transactions. It's supposed to be something that yields milliseconds response times, at least for most operations. But it models, it stores, and it manages data as a network, as a graph. Right? So no more tables, no more rows and columns, a very different data structure. Right? So let's take a look at that data structure. Euler used to talk about vertices and edges, right? We prefer to talk about nodes and relationships because that's sort of more telling for most people in the data world. And let's sort of try to understand what those mean, right? The node, I think, is pretty easy to understand. Right? I mean, for people that, I don't know, if you want to sort of relate it to the relational world, what would you compare it with? A row, a record. I was asking the questions to the newbies, Tim. Jesus, man. No, but it's the equivalent of the row, right, of the record. It's an instance of an entity, right? So if I'm storing people, then one person would be a node, right? If I'm storing computers, one computer would be a row, would be a node, right? It's like one row in a table, right? And if you have lots and lots and lots of nodes like that, it's like having lots and lots and lots of single row tables, right? Because each and one of those nodes can have a different structure, right? It can have different properties, it can have different attributes, so that's what you should really compare it to, right? But the interesting part, I think at least, is in the relationships, right? Because all of those nodes, they contain data, but the relationships are actually first-class citizens in the graph world, and they are, equally important at least. They contain data at least also, and they provide structure to these instances of entities, right? So I can say, Rick owns computer, or actually Emil does, but that's okay. You know what I mean, right? Or Rick drinks beer, right? Rick drinks beer, right? So two instances of entities and a relationship between them, right? And those relationships can have properties as well. So let me ask you the same question. What would be the equivalent of the relationship? Tim wants to answer desperately, but cannot. What would be the equivalent of the relationship? You couldn't help yourself, could you? Yeah, it's the join operation. What's that? Yeah, it's the join operation, right?
It's actually the joint table because we can put properties on the relationship. So the joint table is.
So I'd actually take it one step further. It's actually the use of the join table. It's the result of doing the join. That's what you're actually persisting here, right? So, and you're right. You can put properties on them and you can have more attributes on them. But this is super important and super fundamental to this model, right? It's actually these joins, these expensive operations in the relational table, in the relational model, right? That you would always have to calculate, right, at query time, right? So every time you would do a query that would involve more than one table, you would have to go through the join table, calculate the Cartesian product, and come up with a result, right? So it's a calculation, right? That's no longer the case here. The join is just there. You have to find it, but it's actually just there. It's part of the model. You store, you persist, you pre-calculate the result of the join operation, and it's already part of your data model, which kind of already gives you a hint at what these things will be good at, right? I mean, join-intensive queries, right, which are really expensive in the relational model and which actually spawned a complete industry of BI tools. You know what? There's maybe a better solution for those, right? A real-time solution for those, but we'll get to that. So this is how you should compare the both, right? So here's your join table, right? In the middle between your customer table and your accounts table, there's a join table that basically links customers to accounts, right? And in the graph model, you basically have a node for every customer and a node for every account and a relationship for every join operation, right? So very, very similar in many ways, but also very different in the way they behave, at least operationally, and the way you model data. One of the nicest thing I find about this thing is that it exactly represents how you model your data on a whiteboard. If you would ask a business owner to say, how would you store or how do you work with customers and accounts, very likely he would draw something like that. Very unlikely that he would draw something like that. Right, so it's actually a really good fit for the way people think about reality, right? So yeah, graph database, Neo4j using the graph model, JVM based, and like I was saying earlier, many of those NoSQL databases, they actually do away with transactions in order to scale out, and that's actually a really bad idea for a graph database, right? Because what you're doing here is you're storing data and structure at the same time. And if you're not ACID, it's super easy to to mess up the data. So it needs to be transactional. I mean, there's a lot of people in the industry that say, no, we can do a non-transactional graph database. Well, good luck, right? That's what I say. Because it's really easy to mess it up. It's got lots of wonderful Java APIs for people that really want to go high performance. But the nicest thing that I think has been added to graph databases in the past couple of years is actually the declarative query language, right? So it's all about, we're really trying to learn from SQL, right? What obliterated the network databases in the 70s and 80s was not that they had an inferior model or anything. It was that in order to interact with a network database in the 70s and 80s, you had to be a COBOL programmer. And what's that? Not for you, but for some people that was actually really difficult. And it's very, very easy to understand that as soon as you need to be a programmer to interact with data, right, it becomes a lot more difficult, right? So SQL opened up, a very wide audience of people, like me, with a lot less brain cells, but that can actually deal with business problems, but not so much, how to develop software, right? SQL opened that up for the relational world. Cypher is opening that up for the graph world. A declarative query language. You declare what you want, the database has to figure it out, right? Super powerful, super interesting. It uses the labeled property graph model to store its data. I've already touched upon most of these things, right? So we've got our nodes representing instances of entities. We've got our relationships representing the join operation, right? Both of them can have attributes, can have properties, can have weights, right? And we're actually going to provide a little bit more structure to that graph model by labeling the nodes. And this was something that we didn't do before. This is something that was added in the last couple of years, but it's really a fantastic tool, both for the end user and for the database itself, because it tells you more about the data that you're storing, right? You're giving away information about how the data is structured so that the database can actually behave more intelligently, right? So those are the labels. Labels you should really compare to like Gmail labels or Evernote tags or something like that. It's a rubber stamp where you say, this thing is a book, this thing is a reader, this thing is an author, and guess what? Some people can be readers and authors as well, right? So you can have more than one rubber stamp, right? So that's the labeled property graph. Let's talk a little bit about graph querying, and I'm conscious of time, and I want to show you a little bit of a demo as well, so make it tangible. Querying graph, I mean, the most important thing for you to take away there, I think, is the fact that there's lots of different types of queries that you can run against the graph database, but essentially they usually fall into two big categories. One of them is a category that is not so good for a graph database. The other one is really good for a graph database. It's the difference between local and global queries, right? And at small scale, this really doesn't matter that much. At large scale, this really matters, right? Global queries are your typical OLAP style operations. right? Where you're looking at the entire network and you're trying to do something with that network. You're trying to find new structure. You're trying to calculate rankings. Whatever you're trying to do, you find clusters, communities. Whatever you're trying to do, but you have to look at the entire network in order to do the operation, right? And those are typically operations that you don't do between a web request and a web response, but you do them between dinner and breakfast, right? So they take a little bit longer. Not just in Neo4j, right? In any database and also in any graph database, right? So they are actually much more labor intensive, I would say. What the graph local queries offer is this idea of contextualizing your queries and making them touch only a very small part of the data, right? So you essentially, by anchoring your query to a part of the graph, right? I always picture myself, flying with my jetpack over the network that's lying out in front of me. I used to say parachute, but I think the jetpack is just much nicer. So I take my jetpack and I fly over the network, and then I see something that interests me, and I land on that thing. I anchor on that starting point. From that moment onwards, I have locality. I have a starting point in my query. I have contextualized my query, and I know that this query is unlikely to touch the entire graph. It's only going to touch the part of the graph that is connected to the starting point. So you immediately dramatically reduce the scope of any potential question that you might want to ask. Right? And that's really powerful, right? Because all of a sudden you only need to do like hundreds of evaluations rather than billions and zillions and whatever, right? You're not going to touch the entire network anymore. Super powerful, super important. Also, if you want to get high performance, then locality is probably your friend, right? And how does that work? Well, once I've got locality, I'm going to define a pattern that I'm going to anchor on that local point in the graph, right? So locality, let's say that I want to start over here, right, at the center of this little network here. And then, using Cypher, using something like a query language, I'm going to define a pattern that says, okay, I'm looking for things that are connected in a certain way. Blue connected to orange, orange connected to green, blue connected to green, right? Note that the directions are important, right? The directions of those connections, they can be important. You can ignore them if you wanted to, but they are important. So what is going to happen if I'm going to run this query is, first thing, it's going to anchor and zoom in on this guy, right? I can formulate my query by saying, anchor on every blue guy, but let's just assume I'm going to anchor on this guy over here. Next thing it's going to do, it's going to start spinning around, right, with all the information that it's got from its indexing and blah, 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 blah. It's going to start spinning around and trying to find, if there's a matching pattern connected to this starting point. And it's going to say, yep, that's one. That's clearly not a match. That's another match. That's another match. This is clearly not a match. Right, so it will find 3 matching patterns, put them in the result set, and return those to the end user. Right? These guys over here clearly match the pattern, but you will never even see them. As long as you anchor to this blue guy and only that blue guy. If you anchor to every blue guy, of course, this is going to return as well. Right? But if you anchor to this guy and only that guy, make it local, then you're going to only have 3 matching patterns. Right? So you need locality, or as much locality as you can get, right? And you need a pattern, something that you can describe in this form or close to that. Does that make sense? I think this is a good time to show you something. Or not. Or I could talk about how to mess up an Neo4j project, but that was my plan B. Any questions so far? You know, finding all things is probably not the, well, finding all things, you can do that, you can perfectly do that, but that's typically the type of query that will take a little bit longer because you're going to touch more in the graph. How do you find your starting point? Well, that's a really good one. Thank you for asking that. So, I mean, yeah, how do I get this blue guy, you know? If I've got zillions of nodes in there, how do I find the starting point? How do I take out my jetpack and find the starting point? That's where indexing comes in, right? So if you look at what I said here, right, is basically saying you parachute into the graph, jetpack into the graph, by doing an index lookup, right? So Neo4j, at least, it has this indexing system that is part of the database, right? Which allows you to say, well, I'm going to land on these types of things, right? So these are the things that you should be indexing. No, I don't think so. No, the indexing is really to anchor your query. You know, where are you going to start, right? So you would say, I want to find, let's say that you would want to look for this pattern, right? But you would only want to look for this pattern where you have blue guys with a weight of 100 kilos and more, right? So what the first lookup, the anchoring lookup would do is it would say, give me all the blue guys, right? With this attribute smaller than or bigger than 100 kilos, right? And that would give you, out of your zillion sized database, it will give you, I don't know, 100 returns or maybe 1,000 returns, right? For each and one of those 1,000 returns, it would then evaluate, do I have this pattern matching, yes or no? Yeah, it's the scene underneath, yeah. So that gives you the starting point. Now, the thing that's different about other databases, I think, is, you know, once you've got those starting points, we don't touch indexes anymore, right? You just, I mean, the actual pattern matching, this thing, right? That does not need to use indexes anymore, right? Anchoring to the blue guy, you want to use indexes. But this hopping around here, trying to find that pattern, does not use indexes anymore, which is super powerful because every time you touch indexes, you're literally slowing down your query. Right? So this is literally a pointer chase. You know, finding those patterns is nothing else but a pointer chase. Right? So that's what finding 1,000 of these guys will require indexing. Matching the pattern typically doesn't. Does that make sense? So, and then obviously, you know, these types of operations, you know, finding the top 1,000, whatever, those are likely to touch more of the graph, right? And those are likely not to be like your sweet spot millisecond response time type of questions, right? The more you can make it local, the better it is for the query performance, right? And I'm not saying that we couldn't do it millisecond time, you know, it all depends. I sound like a consultant there, but you know, it really does depend on the actual implementation. But the more local it can be, the better for the query. But usually, you know, lots of people want local queries. You know, you're dealing with one user, you're dealing with, you know, one computer, or you're trying to analyze, you know, behavior in one point in the network, you know, of, you know, trains, of electricity, or whatever it is, you know. You see what I mean? Lots of questions are actually very local. Not all are, but yeah. Okay, so I wanted to show you something because you know what? It's been 40 minutes and I haven't talked about beer yet, so that's very much against my habit. So I kind of want to illustrate how this works by showing you a little demo. I've got 5 more minutes, Mikael? 4. Okay. All right. Quick one then. Quick one. So this, what I did is 3 years ago is, you know, when, no, 2 years ago, I think, when people started to I started to present Neo to customers, I worked with this database of Doctor Who characters, right? And very, very cool, and lots of developers loved it. But the problem is, I have never seen a single episode of Doctor Who, so I couldn't really intelligently talk about it. Maybe that's my problem.